Welcome to The Explainer. We see concrete pretty much everywhere, but how often do we really think about what's in it? Well, today we're going to pull back the curtain and look at the secret chemical ingredients, these things called admixtures, that give this everyday material some serious superpowers. I mean, just imagine for a second, what if concrete could stop rust dead in its tracks? Or what if it could prevent itself from cracking? Sounds impossible, right? But it turns out it can. And no, it's not magic. It's just some really, really clever chemistry.
All right, so let's jump right into our first big problem, the whole flow versus stability thing. Picture one of today's crazy complex skyscrapers, or a tunnel just packed with reinforcing steel. You've got to get concrete into every single nook and cranny, so you need it to flow almost like water. But how do you do that without the whole thing just falling apart? Like a bad salad dressing where all the heavy stuff sinks to the bottom?
So when you make concrete that fluid, which, don't get me wrong, is awesome for pumping it and getting it into tight spaces, you run into this huge risk. All the heavy bits, the gravel and sand, they just want to sink right to the bottom. This is a thing called segregation, and it's a disaster. It can completely ruin the strength of the entire structure. So what's the fix? Well, it's a special chemical called a viscosity modifying agent, or VMA for short. And honestly, the best way to think about it is like a soup thickener. Seriously, it's basically a type of water-soluble polymer, kind of like a gum that you add to the mix. Its whole job is to just hold everything together and keep it from separating. Okay, but how do these things actually work? This part is so cool. When the concrete is just sitting there, not moving, these long polymer chains inside the VMA are all tangled up with each other. It creates this network that holds all the heavy aggregate in place. But, and this is the brilliant part, the second you start to pump it or pour it, that force makes the chains straighten out and align. And just like that, the concrete flows like a dream. It's just genius. And get this, you need a tiny amount of this stuff to make it work. We're talking as little as 0.03% by weight of the cement. That is next to nothing. It's like a tiny pinch of chemical magic that makes a world of difference. And this is a big but. You have to be super careful. If you add even a little too much, you're looking at some pretty disastrous side effects. See, these VMAs are basically a type of sugar, and if you overdose the concrete with it, it can completely stop it from setting. I'm not kidding. You could end up with a soupy mess that just refuses to harden for up to a week. All right, let's switch gears and talk about problem number 2. This is something I guarantee you've seen a million times. Those cracks that always seem to show up in concrete as it dries. And it's not just about looks, right? This can be a really serious structural issue. So why does that even happen? Well, it all comes down to water. Inside fresh concrete, there are these tiny microscopic pores filled with water. As that water starts to evaporate, it creates this incredible force called surface tension. And it's so powerful that it literally pulls the walls of those little pores inward, creating this immense stress inside the concrete. Eventually, something's got to give, and crack, it just tears itself apart. So how do you fight that? Well, engineers have this clever trick up their sleeve called shrinkage-reducing admixtures, or SRAs. And what's so smart about them is that they don't even really mess with the concrete itself. Nope, they go after the water. Their one and only job is to lower the surface tension of the water in the mix. And you can see the difference right here. Look on the left, that's regular water. High surface tension, pulling super hard on the pore walls as it dries, boom, you get cracks. But on the right, once you add the SRA, the water's surface tension is way lower. It's like it's pulling with a gentle tug instead of a violent yank. That drastically cuts down on the internal stress and you get way fewer cracks. It's that simple and that effective. Okay, on to our third major headache, and this one is a silent enemy. It attacks from the inside out. I'm talking about the rust that forms on the steel reinforcement, the rebar, that's buried deep inside the concrete. This is a huge deal, especially for things like bridges near the ocean. And really, silent killer is the perfect way to describe it. When water and salts manage to seep into the concrete, they get to the steel rebar, and it starts to rust. Now here's the crazy part. As steel rusts, it expands a lot, and it does so with such incredible force that it literally cracks the concrete open from the inside. Left unchecked, this can lead to total catastrophic failure. So what's the defense? We fight back with another class of chemicals called corrosion inhibitors. You add these to the concrete mix, and they basically act like a personal bodyguard for the steel. They create this little protective bubble around the rebar, a chemical shield that fights off all the nasty stuff that causes rust. And what's really cool is they have a few different strategies for doing this. It's like a multi-pronged attack. So one way is by forming what's called a passivating film, which is just a fancy way of saying a protective, non-reactive skin right on the steel. Another tactic is to be an oxygen scavenger. They literally go around and chemically grab all the oxygen before it can cause rust. And a third way is to make the concrete right around the steel waterproof, basically building a raincoat so moisture can't even get there in the first place. Okay, so now we're going to venture into some, let's call it next level stuff. We're talking about admixtures where the marketing claims start to sound almost too good to be true. Like they're really pushing the boundaries of what you'd think is even possible. And what's interesting is that even the source material for this explainer throws a little side-eye at some of these claims. You hear about things like crystalline waterproofers that are supposed to grow crystals to fill in any new cracks. Essentially, self-healing concrete. And yeah, you can't help but think, really? Does that actually work? And this brings up a really important point. There can be a huge gap between the marketing brochure and what happens in the real world. You'll have manufacturers claiming their chemicals can travel through solid, hardened concrete to find and protect the steel inside. But when you look at the lab results, they're kind of all over the place. And even worse, there have been major projects, big ones, that have had serious water leakage problems, even though they use these so-called advanced waterproofing systems. Now, while we're on the topic of these advanced materials, there's a quick but super important distinction we need to make. You'll hear two terms, polymer modified concrete and polymer concrete. They sound similar, but they are totally different things. Polymer modified concrete is just regular concrete with a polymer, like latex, mixed in to make it a bit more flexible. But polymer concrete, that stuff has zero cement in it. It uses a polymer, like epoxy, as the actual glue that holds it all together. It's a completely different beast, used for really specialized things, like heavy-duty industrial floors. So, okay, we talked about all this wild, complex chemistry, all these amazing additives. But at the end of the day, what's the one thing that matters most for making sure it all actually works on a real construction site? And the source material could not be more clear about this. You can't just read the label on the bucket and hope for the best. It says flat out that without doing your trial mixes, without actually testing it, you have no idea if your specific combination of cement, sand, stone, and chemicals is going to work. None. And that right there is the key takeaway. Yes, these chemicals can do amazing things, but every single time you add a new ingredient to the recipe, you're adding another layer of complexity. You're adding another variable that could throw everything off. It's another chance for things to go wrong if you're not super careful. So what's the bottom line? Look, these specialty admixtures are seriously powerful tools. They can solve massive engineering problems. But, and this is the important part, their success is not a guarantee. They're not a substitute for good, solid engineering, and most importantly, thorough testing. There's no magic bullet that solves every problem. There's just complex chemistry that you have to understand and manage properly.
It kind of makes you look at a plain old sidewalk a little differently, doesn't it? I mean, if a material we think of as being so simple, concrete, is actually this insanely complex, it just makes you wonder, what other simple materials that we see every day are hiding these incredible secrets right under our noses?